Today, we're going to demystify bit manipulation. Our goal is to move past seeing these things as magic tricks and instead build a solid, logical foundation, right from the ground up.
So no fluff. We're going to build this thing up piece by piece. So you don't just memorize patterns, you actually understand the system.
And really, that's the core question, isn't it? A lot of people see these operations as just a bag of clever hacks. But by the end of this, I think you'll see it for what it is, a predictable, logical system that you can reason about from first principles.
Okay, let's start with the absolute foundation. You see, to really get bit manipulation, you have to stop thinking about numbers as these abstract ideas and start thinking about how they're physically represented inside the machine. This table, this is the ground truth. Every single integer is just a pattern of on and off switches, we call them bits, and each one has a value based on its position. So when we do bitwise operations, it's not some abstract math. We are directly manipulating this physical structure.
Now you really want to pay close attention to this formula. This is 2's complement. It's the system that computers use to represent negative numbers. And honestly, understanding this one single definition is the key that unlocks almost every bit trick that involves negative values.
And that's a super important point. Because of 2's complement, the very same physical circuits inside the processor can handle both addition and subtraction. It's just an incredibly elegant engineering solution, not some random hack. Getting this is fundamental.
So now that we understand how numbers are represented, let's look at the operators we can use to actually manipulate them. Think of these as our fundamental tools. And here's your basic toolbox. You've got AND, which is great for checking if a bit is on or for clearing bits. You've got OR for setting bits or combining them. You have shifts for just moving bit left and right. And then there's XOR, which has some really special properties.
The real beauty of XOR is in these properties right here. Since anything XORed with itself becomes 0, the operation is perfectly self-inverse. It cancels itself out. This reversibility makes it incredibly powerful for things like toggling a state back and forth, or for making duplicate numbers in a list just disappear.
Okay, next up, structuring with masks. This is where we start to combine our tools to create structure. And this is a really crucial conceptual leap because it's where an integer stops being just a number and becomes a super compact set of Boolean flags. We call this a bit mask.
And these 4 operations are basically what you'll be doing constantly. To work with any specific bit, say the ith bit, you first create a temporary mask that only has that bit turned on. That's what 1 less I does. Then you just use your tools. OR to set the bit, AND with an inverted mask to clear it, XOR to toggle it, and a simple AND to check if it's on.
All right, now that we have the fundamentals down, we can look at a few common patterns. And these are the ones that might look like magic at first, but you'll see they are just direct, logical results of the rules we've already set up.
This is probably the most famous one, x and minus x. So how on earth does it work? Well, just remember that minus x is the same as shoe x plus 1. So what happens is you flip all the bits of x, then you add 1. And that has this really neat effect of flipping back all the trailing zeros up to and including the very first 1 bit. So when you AND that result with your original x, the only bit that survives is that single lowest set bit.
And why do we care? Well, this little pattern is the engine that drives the Fenwick tree data structure. It's also a super fast way to check if a number is a power of 2. And it's a key ingredient for efficiently looping through all of the subsets of a mask.
So the counterpart to isolating a bit is, well, clearing it. And the pattern for that is x and x minus 1. When you subtract 1 from any number, it flips the rightmost 1 to a 0, and then all the zeros that follow it become 1s. So when you AND that result with the original number, the only practical effect is that you've cleanly turned off that single lowest bit.
And what's really cool is that this pattern leads to a highly efficient way to count set bits. You just apply this x equals x minus 1 operation in a loop, over and over until x becomes 0. The number of times the loop runs is exactly how many set bits you had. It's way more efficient than checking every single bit one by one.
So let's scale this up. How do these simple little building blocks enable some really powerful techniques that you see in high-level problem solving and competitive programming? This is where you see stuff like bitmask dynamic programming. So instead of using some complex data structure to keep track of which nodes in a graph you've already visited, you just use a single integer. If the kth bit is set to 1, it means we've visited node k. This is what lets us solve problems with an exponential number of states, like the traveling salesman problem for at least small inputs. And how do you work with these masks efficiently? Well, this single line of code, believe it or not, is the optimal pattern for looping through every single subset of a given mask. It cleverly uses that x and x-1 logic we just saw, sub-1 and mask, to elegantly find the next smallest submask every single time. It's a perfect example of building a complex algorithm from our simple fundamental rules.
All right, let's put this all together into a final mental model. Because if you can internalize this hierarchy, bit manipulation stops being a list of tricks you have to memorize, and it just becomes an instinct. So here it is, the hierarchy of understanding. At the very bottom, you have binary. That's the physical reality. On top of that, 2's complement is what gives those bits meaning. Then, masks give them structure. Shifts are how we control position. XOR gives us reversibility. And right at the top, patterns like isolating or clearing the lowest bit, that's what gives it real power. Every single layer is built on the one right below it.
You see, when you understand the logic, instead of just seeing magic, you stop asking, what's the trick for this? And you start asking, which tool from this logical system is the right one to apply here? You have the framework now, so the real question is, what are you going to build with it?